Hi, this is a video for my GCSE Electronics students, could also be of interest to A-level students and anyone else who's using Circuit Wizard. That's the program I've got here. But there are also other programs that are going to have similar features that you will be able to apply the same sort of tips and tricks that I'm going to suggest in this video. So what am I going to do? Well, I'm going to have a quick look at this, and I'm going to criticise this and tell you why I don't think this is a particularly good layout. And then I'm going to encourage you to make stuff that looks more like this instead, which is actually functionally exactly the same as that, okay? But just it's sort of like exploded out, broken up in subsystems, and in fact that's what you need to do anyway for your school projects. So let's have a quick look at this, because I know there's lots of people who think this is okay. And I will also suggest a few things that if you wanted to stick with this sort of layout, you could do to it to improve it. So first of all, I suppose we'd better just have a quick look to see what it could possibly be. It's just like a bit of a random circuit I've made. Okay, it doesn't actually serve a particular function. But we've got a power supply. Let's call that our power supply. We've got that diode to protect if your batteries run the wrong way. You've got an indicator, power on LED there. You've got 3 switches with their corresponding pull-up resistors there, because that's going to be the digital logic in on those inputs there. And we've got some sort of, buzzer alert or something, and an output LED. I don't know what it's going to be, like a game or something like that, perhaps. Okay. Right. So at the moment, it's not entirely clear what components do on here. So my first improvement would be to name some of the components, not all of them. You don't have to say resistor or whatever, because that's very obvious, but this one's like power LED, so I'm going to write PWR LED, all right, or power on. I mean, you don't even need to say LED because that's very obvious, so power on. So when that lights up, the power is on. Okay, it's quite fine to do that, by the way. Reverse biased flow check. I don't know why I'm writing all in capitals, don't really need to do that. Reverse biased flow section. So, if your labels get in the way, drag them around, okay? So add a few labels, like we could label that one up, I don't know, like game LED or warning LED or whatever it is. Well, what do these switches do? Well, we're going to guess at the moment, but that one does go to a pin which is at the digital input or the reset pin, so maybe we could name that one reset, so maybe input switch is going to reset with the device again, whatever, and maybe that might be like the left button, right button, like in sort of joystick or something. Okay, so it would be perfectly fine to actually rename those as well, or add names to them, name labels. It still doesn't really, to my mind, greatly improve the layout, so what I would suggest is to start using the ground symbol. So let's find the ground, stick that in there. So now that's effectively saying that the negative side of the battery is connected to 0 volts, which is the ground. By the way, ground doesn't actually have to be at 0 volts potential, but unless for some reason it is. So effectively that's 0 volts on that side, and then that's plus 6 volts up there. So we cut out that wire there. Let's cut out some other unnecessary wires. See, that's 0 volts there. So now I'm going to press and hold control and then drag that, and I'm going to have it like that. Okay, so now effectively I've got a connection 0 volts from there to there. Notice I have my ground symbol pointed downwards. Some students are, and some might, tempted to do it like that, or even worse to my mind, the ground is not up in the air. I know it's like nice and short then, but we just don't have a ground symbol pointing upwards. In fact, we never have it pointing sideways. We shouldn't have it pointing downwards. The ground is down. Okay. Right. So that's improved that. We could also make use of some more ground symbols. So, what happened there? Let's just where not copied it. So I could do that. And then maybe I could have another one up here. You hopefully understand where I'm going. You can just make more and more use of these. Let's have one there, and then I could get rid of that, and then let's have one there. And mouse, I've got a wireless mouse, sometimes I don't know which one. There, like so, okay. And then of course you can shorten these wires to shift these things up. Okay, but I'm not going to mess around with it too much. It's better, right? I definitely think it's better. However, you still need to look at it with a fair degree of concentration to realise that's your power supply system with a power indicator. That these are all your inputs with their associated resistors, and yeah, you just need to study it a bit. Okay. Now, in GCSE and A-level electronics coursework, you are supposed to split your project up, or you're supposed to design it as separate subsystems. Each one of the subsystems is going to have like a defined input, process, and output. Even whether that's a switch. Like a switch has an input physical. Physical input, pushing on the switch, and then it's going to have a predictable output. And yeah, anyway. So ideally, you should. Well, not ideally. You have to for coursework. You have to split things up in subsystems. Now, the easy way to do that is actually to do the designs right from the start as separate subsystems. So, what you ideally you're going to have something like that, and I'll show you how we get from this, or rather never start with this, but we actually do it from scratch. So let's move my this out of the way. And first of all we need to get that, well, you can do it many different ways. In fact, let's start with power supply. Okay. So 6 volts was my power supply in the example, and then I have a ground rail, not ground rail, ground symbol. And then what I'm going to do, I'll go to connectors and get a terminal. This isn't quite the same power supply you saw a moment ago, but I'm going to build it to that. Okay. And so you call that my power supply system. In fact, it wouldn't even hurt really with it to call it supply system or subsystem or whatever you want. Okay, subsystem. Now, so if I run the simulation, we're in voltage levels at the moment, just normal. If you hover over the line, you'll see that when it's running, it's 6 volts. Okay. By the way, you might want to have a power switch in your power supply subsystem. That's up to you. But we had the diode. I don't know if you remember, we had a diode to protect the rest of the circuit in case the battery was put around the wrong way. So let's just bang a diode in, which we can find in there. And rotate left, Control L, and stick a diode in. Now, the diode should have a forward voltage drop. This is a silicon diode, so a silicon diode should have a forward voltage drop of 0.6 to 0.7 volts. So if this is 0 volts and then we increase by 6, so we're down at 6 volts, and then if we drop by say 0.6, then that would be expected to be 5.4. It's not going to be, but I'll explain why in a bit. Let's just have a look. So up here we're predicting that's going to be 6, and down here with reference to the ground it's going to be 0, and here we said 6 on here, so this is a 5.4, but it's not, it's still 6. In other words, we haven't had any drop there at all. So why? Well, what you need to do, you need to understand, so I did a quick Google search of the forward characteristics of the silicon diode, okay? Or the characteristic curve. So I searched silicon diode characteristic curve, and hopefully what you will see is that we've got current on the vertical axis and voltage on the horizontal, and you'll see at low current, so low current down here, we have no voltage drop. Yeah, okay. Now, when you have when you get say 0.7 volts, you're going to have to have a current going through, because without the current you won't be able to get the forward voltage drop. So if, for example, you've got like a forward voltage drop of say, like, I don't know, like about 0.1 volts or something like that, not what you were expecting, so you're expecting 0.6, it's because you haven't got enough current going through. Once you have more current going through, then you can have more of the forward voltage drop. When you have sufficient current going through, then you'll have the expected voltage drop of about 0.7, 0.6 or whatever. Okay. So we need to actually draw a load. So we need to actually have current. I mean, if you have a look at current view, you'll see that there's no current flowing because you actually circuit wizard will simulate the charge flowing. So what we're going to do, we're going to add something which is going to draw a load from it. So we go to resistors, and let's have LED as well. It's really nice to have an LED in your power supply circuit, because then you can see when it's switched on, and also if you've got a short circuit, sorry, excuse me, if you've got a short circuit, if you've got, I'll try again, if you've got a short circuit, then your LED will go out. Now let's just quickly think, that's going to be 5.4 volts up there, and then we get down to 0 volts here, so we've got a potential difference from here to here of 5.4 volts. 2 volts will be used on the LED, so that gives us, what did I say, 5.4? So that gives us 3.4 volts to drop across the resistor, and we want about 10 milliamps to flow down this branch, so that's going to be 340 ohms, because 3.4 divided by 0.01, 10 milliamps, okay? That gives us 340. There's no such thing as a 340 ohm resistor as far as I'm aware. Oh, I'm sure you can probably get them from some specialist, but probably use like a 330 or let's say 390. So it's not really critical at all. So let's change that. So 390. And now if we run the simulation, LED lights up, that's good. And if we hover over here, yeah, now the voltage is 5.41, so close to what we were expecting. That's my power supply system done. Now, if you're doing this for GCSE, you're going to have to do predictions on how it's going to work, and also how you will test it. Now, you'd have to test it both, you should test it if you can, virtually in simulation circuits, and also break all that up. That's not exactly a difficult circuit or subsystem to test with multimeter, or you could use one of the USB oscilloscopes. Right, so that's the power supply. What are we going to do next then? Let's do our microcontroller. So let's grab ourselves a microcontroller. Never use these ones, alright? Don't worry about why, just don't. Use the dual inline ones. Grab that, and so we need a power supply. So really what we're effectively saying is we need to connect that up there, okay? But we're not going to do that. We're going to name this. I'm going to just give it some random name. Let's call it my supply. Okay, I'm sure there's a better name than that. There are, by the way, electronics engineers will have their own naming conventions how they name nets. This is going to be a net. And do I have a convention? No, I don't particularly. But having a convention would be a good idea. Maybe I'll give you a few ideas as we go through this. So because we've got exactly the same name on the net, this invisible connection between, so effectively that's now connected across. Let's have this like so. So now the power supply is going to be connected via the diode through this named net, and then goes through the microcontroller and down to ground. And in fact, we could possibly, no, right, okay. The reason I just click simulation and it comes up with that, the reason for that is because we've got a microcontroller in the flowchart, this program. So now let's go back to that. Yeah, okay, let's run the simulation. And so that is 5.41, so that will also be 5.41, yeah, which it is. There is a tiny current, 270 microamps. We probably won't be able to see anything on that. It's going ever so slowly, okay, in the simulation. Right, so what else should we do? Let's do a switch, okay? So we need to have switches. By the way, that's now another subsystem, all right? So you see how simple the subsystem is. So let's have a switch. I'm just going to control drag that, and I'll have a resistor. I'm going to use pull down resistors. So what that means is the digital input is going to be pulled down to logic low until I press this switch. Let's change that to a 10k resistor. and we need a switch, obviously. There we go. Let's rotate that. Well, I hope you find the videos useful. If you do find them useful, please do subscribe and like. I tend to do them late in the evening. You can see that. Hopefully they're of use to my students and to anyone else. So if you do like them or if you want to give feedback, then please do. Right, okay, so this is going to be my switch subsystem, but I need an output from this switch subsystem, which then becomes an input into the microcontroller. So I'll just control drag that and I'll rotate that. It's a good idea to have the output of something going like on the right hand side, like that way, and then that becomes an input in the next. Okay, so put that there. What am I going to call that? Maybe that's going to be the reset switch. So I'm going to call that one the reset. And then so now I'm going to rotate that. I mean, there's various ways you could do it. I mean, if you wanted, you could have it like there. If you wanted, I find it gets a bit congested if they're like that. So it could work. But what I'm going to do, I'm just going to rotate it left-wise like that. Okay, it doesn't have to be like that. It's just like my preference. So now, if we hover over that, you'll find that's 0 volts. Okay, so that one's going to be 0 volts as well. That, okay. And then if you press that, then that voltage is going to go up. Of course, I can't press that with the mouse and also hover over there. If we go to voltage levels, hopefully you'll now see that that reset, this thing here, is going to logic high or higher voltage. High voltage, I should say. We're looking at voltage levels, not logic levels at the moment. When I press that switch, the reset here, that's going as well. Okay, so that is working. You could, if you want to, go to logic levels, so you'll see that's a logic low, and then when you click it, and it changes this. You see that's green, and then it changes red. Okay, so yeah, all of that works. You can also use the voltage. You can click that. You can add in voltage probes and things as well. I'm not going to do that. So I'm not going to do all the switches, but basically once you've got one switch subsystem done, you can just copy it like that, and then maybe that's going to be left. Actually, I'm going to name it B. I'm going to have a naming system BTN left. So really, I should have probably called the other one like BTN reset. Not going to bother now to change it, but anyway, you have your own naming system. And so I'm going to just put that one there, and then so like, oh, hang on, didn't click on. There we go. Okay, so then you can set up all of your switch subsystems. I would probably call that one my microcontroller subsystem, and then I could call this one, or these ones, I could call them input switch. So okay, with that. Right, hopefully that makes some sense. Doing the outputs is no more difficult than anything I've done so far, so let's just have a quick look at that. Yeah, you just do them like that. Okay, it's fairly intuitive. I don't think that'll be a problem in you doing this on your own. Is that of any use? I hope it is. I think if you study it, you'll understand why. Actually, that one's not too bad after you put the grounds in. But if you remember what it was like originally, it's just like not a good idea. You'd be much better off with having something like that, which, let's just get me out of the way. Then you can then very easily understand what each subsystem is, and you can test each subsystem as well. Okay, 19 minutes. I got that in just under 20 minutes, so it's still long, admittedly. Maybe some of you managed to watch 5 minutes without getting bored. Thumbs up, and see you again. If you're one of my students, see you in class. Okay, that's it.